Right now, like 11.9 light years away, there is this toxic, crushing alien world. It's over 7 times the mass of Jupiter, completely shrouded in darkness, orbiting way out from its host star. But floating at the very top of its massive, swirling atmosphere are the exact same wispy, delicate ice clouds you'd see out the window of a Boeing 747 on a summer day here on Earth. Welcome to today's deep dive.
Yeah, it's quite the visual to start with.
It really is, and we're looking at some incredibly recent research published on technoscience.net today. It details findings from the Astrophysical Journal letters that came out on May 15, 2026.
Right, and the core mission today is really to figure out how this one distant planet is actively breaking our mathematical models of the universe.
Exactly, and why finding something as mundane as an Earth cloud in such a hostile environment is just, fundamentally changing the hunt for alien life.
It forces a complete reevaluation, honestly. We're looking at a situation where human observation has collided with theoretical assumptions, and the assumptions lost.
The assumption's totally lost.
Yeah. This one discovery regarding a missing chemical signature is requiring the scientific community to painstakingly rebuild the models we use to understand the cosmos.
Right, so to understand why a few ice clouds are tearing down decades of astronomical modeling, we have to start with the planet itself. The target here is Epsilon Indi Ab. Astronomers classify this as a super-Jupiter.
And the numbers on this thing are hard to wrap your head around.
Seriously. It has 7.6 times the mass of our Jupiter, but the diameter is essentially the exact same. So we aren't looking at a planet that takes up a vastly larger footprint in space, but it is packing nearly 8 times the amount of matter into that exact same volume.
Which means the density is immense. When you cram that much mass into a constrained volume, the gravitational pull just scales up dramatically.
Okay, that makes sense.
Right, and that extreme gravity compresses the atmospheric gases down to pressures that we simply do not experience on rocky planets like Earth.
Wow. Okay, and its location makes it even weirder. Epsilon Indi Ab orbits its host star 4 times further away than our Jupiter orbits our sun.
Yeah, so because of that massive distance, it officially falls into the category of a cold Jupiter.
But here is the contradiction in the data. The surface temperature readings coming off this planet range from 200 to 300 Kelvin. For those of us using Celsius, that's anywhere from -73 degrees to a positively balmy 27 degrees Celsius.
Which is around 80 degrees Fahrenheit, right?
Okay, let's unpack this. If it's orbiting 4 times further away than Jupiter, sitting out in the dark, freezing outer limits of its solar system, it should be an absolute cosmic icebox.
It really should be.
How does a planet sitting in the deep freeze of space reach 27 degrees Celsius? It's like finding a hot water bottle in a freezer that's still warm.
That's a great analogy. What's fascinating here is that the heat we are detecting isn't coming from the host star at all.
Oh, really?
Yeah, at that distance, the star is little more than a painfully bright point of light in the sky. It provides almost zero thermal energy to the planet. The heat is entirely internal.
Wait, residual heat?
Exactly. It is residual thermal energy left over from the planet's own formation.
But this system is presumably billions of years old. How does a planet just hold on to heat for that long without cooling down into a solid block of ice?
Well, it comes down to the sheer mechanics of gravitational collapse. When a super-Jupiter forms, you have an unimaginably massive cloud of primordial gas and dust collapsing in on itself under its own weight.
Okay, I'm with you.
And as all that material falls inward, the friction and compression generate a staggering amount of thermal energy. Because Epsilon Indi Ab is so massive and dense, its atmosphere acts like the ultimate cosmic thermos.
Oh, so the heat is just trapped deep in the core.
Exactly. So even billions of years later, as the planet orbits in a freezing vacuum, it is still very slowly radiating that ancient primordial heat outward from its center. It generates its own localized climate.
So it's basically a giant ember slowly cooling off in the dark.
That's a perfect way to put it. And that internal heat engine is what makes observing Epsilon Indi Ab so incredibly difficult, but also so revealing.
Which brings us to how we are actually looking at this thing. If it's just radiating a faint internal heat, and it's sitting right next to a star that is vastly brighter, how do we even see it?
It's definitely a massive challenge.
I mean, it seems like trying to spot a single firefly hovering right next to an industrial searchlight.
That is exactly what it's like. To capture that firefly, astronomers used the James Webb Space Telescope. Specifically, an instrument on board called ARI, which stands for Mid-Infrared Instrument.
Right, and MRI doesn't look at visible light, it looks at heat signatures.
Precisely. But to prevent the James Webb from being completely blinded by the host star's searchlight, they have to use a technique called direct imaging paired with a coronagraph.
Okay, I've heard of coronagraphs used for looking at our own sun, but doing it for a star 12 light years away sounds like a totally different level of engineering.
Oh, it requires microscopic precision. A coronagraph is essentially a physical mask built into the telescope's optics. It is precisely aligned to physically block the blinding photons coming from the host star.
Got it. So it eclipses the star artificially inside the telescope.
Right. By doing that, the overwhelming glare is suppressed, allowing the incredibly faint infrared glow of the planet to become visible to the sensors.
So scientists use this incredible coronagraph technique, basically holding a thumb up to block a glaring sun so you can see a firefly next to it. And when they look at this planet, they're expecting to see an atmosphere dominated by ammonia.
Right, the fundamental physics of a gas giant at this specific mass and temperature dictate that ammonia must be present. It is a chemical inevitability.
Okay.
So the MRI instrument is tuned to look specifically at the 11.3 micrometer wavelength.
Okay, stop right there. The data emphasizes this 11.3 micrometer wavelength. Why that exact number? What makes it the magic number for ammonia?
This is where the science of spectroscopy comes in. Every molecule in the universe vibrates at specific frequencies.
Okay, making sense so far.
When light, or in this case infrared heat energy, passes through a gas, the molecules in that gas absorb very specific colors or wavelength of that light.
Ah, I see.
Ammonia molecules vibrate in a way that perfectly absorbs infrared light at exactly 11.3 micrometers. So when astronomers look at the spectrum of light coming from a planet, they are looking for a dark gap at that specific wavelength.
Because if there is a missing slice of light at 11.3 micrometers, you know with absolute certainty that ammonia is present in the atmosphere absorbing it.
You got it. But the anomaly they found changes everything. When the James Webb looked at Epsilon Indi Ab, the ammonia signature was missing.
Wait, missing entirely. But if the planet is a massive gas giant and the physics absolutely dictate that ammonia has to be churning around in there, how could our most advanced telescope just miss it?
Well, that's the big question.
I mean, if the ammonia is physically there, why is the 11.3 micrometer gap missing? Is the planet broken? Or is our math broken?
We have to rely on the scientific method of deduction here. If the math guarantees the ammonia is present, but the sensors cannot detect its absorption signature, the chemical hasn't vanished.
It's just hiding.
Exactly. It is being obscured. Something physically massive and optically opaque must be situated much higher up in the atmosphere.
Oh, so it's sitting above the ammonia layer, physically blocking those specific infrared wavelengths from escaping the planet and reaching the telescope.
Yes, exactly.
So instead of a heavy blanket thrown over a flashlight, whatever is up there is acting more like a massive thermal mirror.
That's a really good way to visualize it.
It's sitting high in the atmosphere, bouncing the infrared signature of the ammonia back down into the planet and shielding it from the James Webb sensors.
That thermal mirror concept perfectly describes the mechanics at play. The ammonia is churning away deep down, but the Webb telescope can only see the reflective surface of the mirror sitting on top of it.
And the researchers figured out what that mirror is actually made of, which is where it gets really interesting. The missing ammonia signature is explained by the presence of thick water ice clouds.
Yes, water ice clouds.
The exact same kind of high-altitude cirrus clouds we have here on Earth, composed of tiny, highly reflective ice crystals, but on a gas giant.
Finding water ice clouds on a gas giant is an extraordinarily rare event.
Why is it so rare, though? Space is cold. Shouldn't ice be everywhere?
Space is cold, yeah, but gas giants are usually extreme in one direction or the other.
Right, like hot Jupiters.
Exactly. If you look at a typical hot Jupiter, a gas giant orbiting very close to its star, the entire atmosphere is roasting. Any water present is entirely vaporized into a hot gas.
So it never condenses, so it never forms distinct clouds.
Right. On the other end of the spectrum, if you have a gas giant that is far from its star and lacks strong internal heat, the atmosphere is deeply freezing.
Oh, so any water just freezes solid deep down.
Yes, it freezes solid deep down in the crushing lower layers of the atmosphere, making it completely invisible from space.
So it's usually either a planetary steam room or a planetary deep freeze. But Epsilon Indi Ab is somehow walking a tightrope between the two.
It exists in a highly specific Goldilocks zone for water condensation entirely because of that internal thermal engine we discussed earlier.
Oh, right, the trapped heat from its formation.
Exactly. This raises an important question about how planetary physics work.
Yeah.
The intense primordial heat radiating from the core pushes materials, including water vapor, high up into the atmosphere.
But as that vapor rises away from the core and gets closer to the vacuum of space, the temperature just plummets.
Right. The pressure drops and the cold of space takes over. Exactly at that boundary layer, the temperature hits the perfect sweet spot. It cools the water vapor just enough to freeze it into tiny, highly reflective ice crystals.
Oh.
And because the planet is so massive, these crystals form a global layer of thick cirrus clouds.
And that global layer of ice is the thermal mirror bouncing the Webb telescope sensors back, hiding the massive oceans of ammonia gas underneath.
You got it.
Here's where it gets really interesting for you listening. We have to picture an unimaginably huge, crushing atmosphere of ammonia gas, but capped off with the exact same delicate, wispy ice clouds you'd see out the window of a commercial airplane on Earth.
It's a striking mental image, for sure.
But discovering an Earth-like weather system on a super Jupiter doesn't just give us a cool mental image, right? It fundamentally shatters the scientific framework we've been using to study the cosmos.
It really does. The data states that current atmospheric models for gas giants simply do not include water clouds.
Like they just aren't in the math at all.
Not at all, because the models assumed water on these planets would either be fully vaporized or locked away in deep ice. The models did not account for this specific temperature inversion.
Where internal heat pushes vapor up to meet the cold vacuum, creating a high-altitude reflective mirror.
Exactly. This one observation conclusively proves that the foundational atmospheric models astronomers rely on are incomplete. They have to be rewritten to reflect reality and account for these localized weather systems.
So scientists now have to figure out how these clouds form, how they distribute around the planet, and whether Epsilon Indi Ab is just a one-off freak of nature or if this phenomenon is happening everywhere.
Right. The mechanics of their formation are still poorly understood.
And to do that, they are looking to the future. The research team is requesting more time on the James Webb, but they're also preparing for the Nancy Grace Roman Space Telescope. That one is slated for launch around 2026 or 2027.
The Nancy Grace Roman Telescope will be a critical asset for this specific problem. It's designed with next-generation chronograph technology.
Oh, so even better than the thumb blocking the sun trick.
Vastly better. If the Webb telescope's coronagraph is like holding up a thumb to block the sun, the Roman telescope's coronagraph is like using a mathematically perfect, digitally adaptive eclipse to block the starlight.
That is wild.
It will be so much more efficient at direct imaging, allowing us to see these faint reflective ice clouds on dozens, perhaps hundreds of other gas giants.
So what does this all mean for you listening? The research points to a much bigger implication here, beyond just categorizing gas giants. Understanding these massive clouds is vital for interpreting signals from smaller planets.
Right.
Why does a water cloud on a super Jupiter affect our ability to find a second Earth?
If we connect this to the bigger picture, gas giants are really our astrophysical testing grounds.
Because they're huge and easy to spot.
Exactly. They are loud, they are massive, and relatively speaking, they're easier to observe with direct imaging than a tiny rocky planet. The ultimate goal of astronomy right now is to find biosignatures on Earth-sized exoplanets.
And just to clarify, a biosignature would be what exactly?
A biosignature is a specific chemical imbalance in a planet's atmosphere that strongly suggests the presence of biological life. For example, finding large amounts of oxygen and methane together.
Okay, why those two?
While in a dead atmosphere, those chemicals react and destroy each other quickly. If we see them coexisting, something like biological life must be actively producing them.
Oh, I see, but I'm guessing these signatures are incredibly subtle.
They are microscopic variations in the light spectrum.
Okay, I see the problem. If we are looking for a microscopic variation on a tiny planet, we need absolute confidence in our mathematical models. And one we're reading on JWST just rewrote the textbooks on gas giants.
Exactly. The models are the lens through which we view and interpret the universe. If our foundational models cannot even accurately predict something as massive and basic as global water ice clouds and a glowing super Jupiter that we can look at directly, well, we stand absolutely no chance of correctly identifying a fragile, subtle biosignature on a dim, Earth-sized world.
Right. If the lens is flawed, everything we look at is distorting. Fixing the models for gas giants is basically a mandatory prerequisite.
It absolutely is.
We have to understand the glaringly obvious weather on the giants, before we can ever hope to recognize the subtle breath of life on the small rocky worlds.
We have to prove we can read the headline before we try to read the fine print.
I love that. To quickly recap how we got here, we started with a massive superjupiter, Epsilon Indi Ab, glowing in the dark with primordial heat from its own violent formation.
Which created an atmospheric mystery.
Right, the James Webb Space Telescope went looking for a massive layer of ammonia and found a missing gap in the data instead. By realizing that ammonia had to be obscured, scientists deduced the existence of a high-altitude thermal mirror made of pure, Earth-like cirrus clouds.
And that one discovery is forcing a total rewrite of how we model planetary atmospheres. From a single missing data point at 11.3 micrometers to a complete paradigm shift in the hunt for extraterrestrial life.
For you listening, this is the ultimate reminder of how science actually operates. It is not just a static textbook of facts. It's a process of constantly testing assumptions and, more importantly, adapting when the universe proves those assumptions wrong.
And the tools we are building right now, from JWST to the upcoming Roman Space Telescope, are accelerating that process exponentially.
It really is an exciting time.
It requires astronomers to embrace the unknown and question their own foundational math, which leads to a fascinating implication to leave you with. If we completely missed something as fundamentally recognizable as a global system of water ice clouds, simply because they were floating on a planet where our models firmly stated they could not exist.
What else are we missing?
Exactly. What other deeply familiar, profoundly Earth-like phenomena are hiding in plain sight out there in the dark, perfectly camouflaged by our own limited expectations?
That is wild to think about. That's all for today's deep dive.